Okay, so let's continue where we stopped last time. So quick recap. So in the last class, I set up this problem of supervised learning, wherein we're given a data set, S, which I'll always denote S. So this is a set of labeled pairs of points. So you have a bunch of instances which I'll denote xi, x1 through xn are the corresponding instances. Sometimes they're called feature vectors, sometimes they're called examples, and so on and so forth. And to each xi we have an associated label which will denote yi. The domain, the set of instances comes from this set which I call the domain set, and the yi's come from a labeled set. And these domain set and label set are known, given to us a priori. However, these xi, yi's, we assume that these are all drawn independently. So each data point is drawn independently and identically according to some unknown distribution pxy. All right, and the goal is to somehow give guarantees on how well you can learn the relationship between x and y given these n samples. And we want these learning guarantees to hold true irrespective of what fpxy is. Okay. We'll also in between consider this special case where y is the relationship between x and y is deterministic but unknown. So y is equal to some f of x, where this f is assumed to be drawn from some class of functions which we call a concept class. Now this concept class may or may not be unknown. When we will distinguish the cases where the concept class is known versus where it is not known. All right. So the most specific case or the most special case is when f belongs to a concept class and this concept class is known. Slightly more general is the case where f belongs to a concept class but the concept class is unknown. And the most general framework is where x and y are drawn IID according to some distribution pxy. Right? And no restrictions are imposed on the joint distribution of pxy. So given this data, our goal is to develop a learning algorithm. So the learning algorithm takes as input the domain set and the label set, which is of course always known. It takes these n IID samples, the data set, and it also takes as input two other parameters. One, the hypothesis class, which is the class of functions or the class of predictors that you can choose from, and a loss function L. And the goal is the goal of a learning algorithm is to output some hs, which belongs to this hypothesis class, such that on average, if you draw a new sample independent of the data set, then the loss is small. So the expected value of the loss corresponding to the prediction made by hs is small. And this expected loss is what we call the risk. And right here I've denoted this h as h subscript s just to indicate that h is a random function that is dependent on s. So for the same learning algorithm, if you give a different data set, then you'll get a different output h subscript s. Right? For example, if you run something like empirical risk minimization, then you would get one particular. So empirical risk minimization is a learning algorithm, and the final, let's say, neural network or linear regressor or linear classifier that you get at the end of training using ERM or anything else is the predictor. Right? So it's important to distinguish between the learning algorithm, which is how we are going to process the samples in order to get the predictor, and the final output, which is a function, which is the predictor itself.
Okay. H consists of only deterministic functions? Or?
So we'll assume that H only consists of deterministic functions. Okay. No additional randomness is required.
Can you do better with the probabilistic function?
Not really, because the metric that we're going to use is expectation. And again, you can use something like the data processing inequality to show that any additional randomness that is independent of the data set is not really going to help.
What if you're trying to model the distribution itself?
Um,
You want P of xy and not a function of x.
So as I said, it's intimately tied to this metric because we want to minimize some expected loss. Now there can be other scenarios where additional randomness may be required even. For example, let's say that you want to simulate pxy. All right. So think of something like a diffusion model. There you need some additional source of randomness. Whereas in this problem of, let's say, classification or regression, any additional randomness will not really help. All right. Okay. So given this very high level framework that we have, there are a bunch of questions that we would like to answer. And these are some questions to which at least we'll provide a partial answer at least in a part of this course. All right. So the first question we would like to address is, what are the fundamental limits of learning? And when I say fundamental limits of learning, how small can you make this risk given, let's say, a bunch of parameters, given the hypothesis class, given, let's say, either the concept class or the distribution, whatever. And also, so firstly, how small can R be? Can it be brought down to 0, or is there a fundamental lower bound to how small it can be? And what is the minimum number of samples that are required to achieve a desired performance? Let's say you want the average risk to be, the risk to be, let's say, 0.1 with probability at least 0.99. Then what is the minimum number of data points that you required in order to get this particular target performance? Because after all, in many cases, the amount of data that you have is fairly limited, right? So it makes sense to conserve the amount of data that we require. So a large part of this course will essentially try to address what is the minimum number of samples, or at least bounds on the minimum number of samples that are required in order to achieve a target accuracy. And the next question, which is a very natural question to ask, is, how does the hypothesis class affect learnability? Because in the end, you don't know much about the data generating process, because we've assumed it's a very general framework. Sometimes you may know the concept class, in which case it may or may not make sense to choose the concept class as your hypothesis class. But if you don't know what the concept class is, then how would you choose your hypothesis class? Or maybe a little more concretely, suppose I give you two different hypothesis classes, which look roughly the same, maybe have the same number of parameters and so on. Then how would you choose one over the other? Is there some fundamental principle? And in order to, when we give answers to these questions, the answers will be based on the assumption that we want to always minimize the number of samples that is required. So we're in the regime where we want to conserve on the amount of data that is required, but we have no constraints on the amount of computational complexity that we have. Right? That's the general framework that we will follow throughout the course. That's the fundamental assumption that we are going to make, right? Because when we talk about, well, we need to impose some constraints ultimately, and it's easier to derive bounds, all right, because of the way we will pose certain problems. The problems will be posed assuming that you have no computational constraints. If you impose computational constraints, then the problem becomes only harder. It doesn't make it any easier. That's number one. Number two, if you want to prove, let's say, that something is impossible, then you want to say that it is impossible even if you don't have any amount of computational constraints. Right? On the other hand, when you want to say that something is possible, then you also want an efficient algorithm that achieves that particular performance. In many cases, you can actually achieve that performance even with computational constraints. but that requires you to develop algorithms and so on. Most of the achievability one can do just by, let's say, designing an algorithm and, let's say, simulating things. All right, you can empirically verify that you achieve the target performance, but in the end, we are interested in bounds. What are the fundamental limits? That's the question that we will address in this particular course. Although the other problem of what is possible, what are the fundamental limits with, let's say, polynomial time algorithms, that's an equally interesting question, but those questions are extremely hard. And till date, many of those questions have not been answered. So let's say that I want to know what is the minimum number of samples required to achieve a target performance, but with polynomial time algorithms. All right, that's a question that's natural to ask. And for most problems of interest, the answer is unknown. There are conjectures that, okay, for certain problems, there is a difference between what can be achieved if you don't have any computational constraints versus if you have computational constraints. But in many of these cases, there's no proof saying that you cannot do this using polynomial time algorithms. All right. So, but in any case, we'll try to study certain measures of complexity of H given two hypothesis classes. How do you say one is more complex than the other? When I say more complex than the other, it means that you need more samples to achieve more data points to achieve the same level of performance compared to the other. All right. And but even before that, the natural question is, can every learning problem be solved? That is, if I give an arbitrary supervised learning problem, then can you always, given an epsilon and delta, can you always achieve epsilon delta accuracy given any number of samples? All right. So that's what we will spend a lot of the time on in the next few classes. But also later on, we want to study some things that become more complex. So we'll see that not every problem can be solved. And so then we need to understand what else can you do. And we'll also try to develop general principles that are useful in practice. All right. So although every algorithm that is designed using learning theory, where we don't assume any computational constraints, they can't be implemented directly in practice, but still they give a lot of insights as to how you should design your algorithm in order to achieve the best performance. So instead of blindly going through and looking for a good algorithm, learning theory gives some general guidelines that, okay, you should basically do this, but minor tweaks and heuristics can be used to maybe slightly improve things. In particular, we'll see how do you do model selection. That is, let's say that you have certain parameters in your hypothesis class, what is typically referred to as a hyperparameter. For example, if you're let's say training a neural network, then maybe the width of the neural network is a hyperparameter, or maybe the size of your convolutional kernel is a hyperparameter. So how do you model this in the framework of learning theory, and how does that affect, if I have a bunch of hyperparameters, then how does that affect the speed of learning, say? All right. And we'll see some other general principles which are used in practice, like cross-validation and regularization and so on, and how this can benefit. What is the general philosophy of using regularization? When should you use a regularizer, and what kind of benefits can this provide? All right. Of course, we'll only scratch the surface of what is known, but we'll still get some insights as to why people do things in the way they do in practice. All right. Great. So now that we have this framework, let's start with we want to understand what is possible and what is not possible. All right. So is it possible to achieve zero risk all the time, or is there a fundamental limit? Assuming that we have all the knowledge that we can possibly have, let's assume that you're even given the distribution Pxy, then what is the minimum risk that you can hope to achieve? Assume that you're free to choose your hypothesis class as you want, and somebody also tells you pxy, then what is the minimum risk that you can achieve? Because this gives a fundamental lower bound to what can ever be done using any choice of hypothesis class or anything else.
So,
Yeah.
in this course we are assuming only three assumptions, right? First, no combination limits. Second,
Correct.
that P of xy is fixed and does not change with time.
Correct.
And third, that training set is IID.
Correct.
Only these three assumptions.
Only these three assumptions are going to be used. All right, so let's suppose that, assume that we are given pxy. So even if somebody tells you what the actual pxy is, then what is the best that you can do? You don't have pxy in practice, but if there's something that can't be achieved even if you know pxy, then you can't do any better if you don't know pxy. All right. So then what is the minimum risk that you can hope to achieve? It's simply, well, what is the quantity that we want to minimize? It is the expected loss, L of h of x, comma y. And if you wanted to know what is the minimum possible, then you just do min over all functions h from x to y. All right. And this is what is called the Bayes optimal solution. So if we are looking at specifically classification, then the Bayes optimal solution has a specific form. So for classification, the Bayes optimal solution, let's call it H Bayes, is equal to the arg max over all y in y of the expected value, or in this case just the probability that y is equal to y given x. So as an exercise, show that H Bayes actually minimizes R, the risk. That is, irrespective of how you choose H, for every other H, R of H is always greater than or equal to R of H Bayes. So obviously this R star is a fundamental lower bound to any learning algorithm. No matter what you do, you can't improve over this. Right? You can't achieve any risk which is less than R star. Of course, this R star depends on Pxy. That's something to be kept at the back of your mind, right? And the one that minimizes or achieves R star, that also depends on the distribution Pxy. So this is one fundamental lower bound to performance. But now suppose that you fix a hypothesis class. Let's say you fix a class of all one layer neural networks with 100 neurons. Then what is the best performance that we can hope for? Because this will also be a fundamental lower bound to performance. You can't do any better than the best H within the hypothesis class, right? So this is something we'll denote R of H star. So H star is, let's define H star as any element that minimizes the expected risk, that is R of H, so the difference between, say, R of H star and R star is that here you're doing a constrained minimization over H within the hypothesis class, whereas here there is no such assumption. This is minimization over all possible functions. Right. So this is the best possible within the hypothesis class, whereas this is the best possible over all possible hypothesis classes. Any questions so far? Okay. So now let's suppose that,
Sir,
yeah,
in the classification we wrote last slide,
here, okay.
the H base of H is a function.
H base is a function, true.
And the right hand side is the function is what is written, R max of Y.
Correct.
So Y is function.
No, Y is a variable, right? So, for example, in the case of binary classification, let's say H base of X would simply be max. Okay, so this would be, let's write it a little more explicitly. So this would be equal to 1 if the probability that y equal to 1 given x equal to little x is greater than or equal to the probability that y equal to 0 given x equal to little x, and it's equal to 0 otherwise. Alright, that's the explicit form of H base. But I mean, at least this form holds true for more general multi-class classification problems. Right? More than two non-binary classification problems.
So classification based on three kind of classification algorithms. One is discriminant based, one is discriminatory based. In discriminant based, we do not calculate posterior probability. So does it also say that discriminant based classifiers are never optimal because it doesn't calculate the posterior probability?
But the question is, how do you get the posterior probability? Right?
We don't calculate it in those classifiers.
Correct. So ultimately it boils down to what you know about the problem.
But here we say that if we know the posterior probability, that's the best.
If we know the posterior probability, then this is the best. True. But in practice, you don't have this.
If we have, that's the best.
If you have, then this is obviously the best thing to do. Under this measure of performance, right? Under, expected loss of, if you want to minimize, basically this minimizes the probability that h of x is not equal to y. Right? For all distributions, among all possible distributions, pxy.
That's what we want, right? Minimize the risk.
That's what you typically, this is what you want to minimize, but then again, maybe instead of the probability of error, you could have some other measure. Let's say cross entropy loss. Your goal is to minimize the cross entropy loss itself. Or let's say squared error loss. So in a regression problem, if you want to minimize the squared error loss, then it turns out that the Bayes optimal solution turns out to be the expectation of y given x. Conditional expectation of y given x is the one that minimizes the mean squared error. So if you change the loss function, then the form of the Bayes optimal solution will also change. But in general, the Bayes optimal solution is always one that minimizes this particular, which minimizes the expected risk. All right. But then again, mostly the lower bound that you would like to shoot for is this particular quantity. Within the hypothesis class, what is the best that you can do? So in fact, in most cases, we'll decouple the two different problems. One is you first choose a hypothesis class, one that you hope to, which sort of approximates pxy as well as possible, whatever that approximates means. And the second, now that you fix the hypothesis class, try to do the best within this hypothesis class. So in fact, let's see, what is the gap to optimal performance in general? It's going to be, so given a learning algorithm that outputs hs, the gap to optimal performance is r of hs minus r star. Right? If you are doing everything perfectly, optimally, then this would be equal to 0. You can achieve this to be equal to 0. But this r of hs minus r star, I can just write this as r of hs minus r of h star, because h star is the best that within this particular class, plus r of h star minus r of hs. I'm sorry, r of h star minus r star. So this excess risk that I have on the left compared to the optimal risk that can possibly be achieved can be decomposed as a sum of two terms. One, within your hypothesis class, once you fix your hypothesis class, how close are you to the optimal solution within the hypothesis class? Right? And this is what is called the estimation error. And the second is the error that you face because you chose the hypothesis class to be H. Right? That's in some sense the modeling error, but it's also called the approximation error. Which is also sometimes referred to as an inductive bias. You made some assumptions on the hypothesis class that it should be so and so. And this is the penalty that you have to pay because you chose a bad hypothesis class H. So in a sense, we can decompose this into two problems. One, you want to minimize the approximation error. The other, you want to minimize the estimation error. But one thing to be kept in mind is that this can't always be decoupled independently. In many cases, there's a trade-off. So one way of reducing the approximation error is to choose a richer class of functions. Is to choose, let's say, H star to be the class of all possible functions. Then you would be able to make the approximation error to be exactly equal to 0. But then if your hypothesis class is too rich, then the estimation error would correspondingly become larger because you would perhaps need more samples to get a particular, to ensure that this quantity is small. Right? If you have too few samples, then R of Hs would be very, very different from R of H star. Conversely, if H is very, very simple, then you would be able to achieve a very small estimation error, but then the approximation error would be very large. So the whole goal of learning is to delicately balance these two quantities. You want something that achieves a small approximation error. At the same time, given the number of samples, you can also achieve small estimation error. So for the first part, in the next couple of lectures, we'll assume that this approximation error is something that we have to live with. We'll fix a particular hypothesis class, and for that given hypothesis class, we'll see how small we can make the estimation error. Right? We'll focus on that one particular term. And later, we'll see the sort of relationship between the two. Is it possible to make both simultaneously small? Or how should you go about choosing a good hypothesis class which is rich enough but at the same time can be learned quickly? Right? So this notion of pack learnability essentially takes care of the first term. So given a hypothesis class, how fast can you learn this hypothesis class?
So,
Yeah.
In the talk you mentioned H star belongs to. So it means that given H star might not be unique.
H star may not be unique. So that's why I use this quantity H star belongs to argmin. Right? There could be two solutions that achieve the same minimum risk. Although the minimum value of the risk is unique, the H that achieves this minimum risk may or may not be unique. There could be two different solutions that achieve the same value of minimum risk. But that's okay. You can choose any one. It doesn't matter. Does that answer your question? Okay. So this notion of pack learnability, sometimes also called agnostic pack learnability, and it says the following. So pack learnability is a property of a hypothesis class. So given let's say x, y, and the loss function, so these are fixed beforehand, we say that a hypothesis class H is pack learnable so we'll say that it is pack learnable if you can achieve R of Hs to be close to R of H star using a finite number of samples. At a high level, that's what pack learnability will refer to. But more formally, so if for every epsilon greater than 0 and delta greater than 0, there exists some positive integer n which depends on n, epsilon and delta. Let me use the following notation instead. N subscript h, so this depends on the hypothesis class, epsilon delta greater than 0, so this n can potentially depend on epsilon and delta. And a learning algorithm that outputs HS satisfying probability R of HS greater than or equal to R of H star plus epsilon to be less than or equal to delta. As long as the number of samples is greater than or equal to this quantity n h of epsilon delta.
So
Yeah.
I just want to just confirm the intuition that we ideally want that RH of HS is greater than equals to R of H star plus eta.
So we want R of HS to be less than or equal to R of H star plus epsilon.
Probability one, but just because sometimes the training error is not a representative of the whole, that's why we don't want that it performs too well on training set, and that's
Correct.
why we want the learning to fail so that it generalizes well.
Yep.
That's why we have a delta margin.
Correct.
It should be at least with the probability of delta, the learning should fail.
No, not really.
Because
So-
our learning is like our objective, right?
So,
Empirical risk.
so- well, it's not that we want it to fail explicitly, but rather that it's not possible to achieve a zero value of delta for a strict positive epsilon, right? Because it could be that the samples that you got is not representative of the true distribution, and therefore no matter how you choose, how well you choose your hypothesis class or your learning algorithm, you could still go wrong because your training set turned out to be bad. All right. For example, if let's say you're trying to estimate the bias of a coin, right? Let's assume that the bias, the probability of getting a H is actually P, say P equal to 0.3, but then you keep tossing with some non-zero probability you will get all heads, right? So even as n becomes large, there is some positive probability. That probability could be very, very small, but still there is a positive probability that you will get all heads. All right, that can still happen. And that's exactly what this delta is designed to characterize, that it's impossible to do well all the time. But given sufficiently number of samples, I should be able to control delta. If I take more and more samples, then hopefully I should be able to achieve R of HS. I should be able to give this amount of confidence with a certain minimum probability, 1 minus delta. All right. So hopefully as I increase the number of samples, as n becomes larger and larger, I should be able to make both epsilon and delta go down to 0. If I am able to do that, then it means that this hypothesis class is pack learnable. All right, does that make sense? So essentially another way of putting or saying that a particular hypothesis class is pack learnable is essentially saying that as you increase the number of samples, you should be able to find a learning algorithm that as n tends to infinity, this epsilon and delta go down to 0. Something would not be pack learnable if, even if you let n tend to infinity, you cannot make epsilon delta arbitrarily small. This epsilon, I could pose it a little differently. I could say that I want probability r of hs greater than or equal to r of h star greater than some epsilon l less than or equal to delta n, where epsilon n and delta n tend to 0 as n tends to infinity. If they don't both tend to 0, then it means that I can't really achieve. So this hypothesis class is not pack learnable.
Basically, we are saying that in the limiting case, you will be able to achieve zero estimation error.
Correct. Effectively, that's what we want. Provided we have enough number of samples. All right. Any other questions? Okay, so we can also restrict this definition to pack learning concept class. So a concept class C is pack learnable So this, when I say a concept class C is pack learnable, it implicitly there is the assumption that the hypothesis class is equal to the concept class. You know this beforehand. Somehow you get this information. If, again, for every epsilon greater than 0 and delta greater than 0, there is some NC of epsilon and delta, some positive integer, and a learning algorithm that takes n samples and outputs HS satisfying probability R of, or in this case, let me see. So for this particular definition, we'll assume that let me state the more general form. R of HS greater than or equal to R star plus epsilon should be less than or equal to delta for all R of H star plus delta for all n greater than or equal to NC of epsilon comma delta. But for binary classification, or in general any classification problem, will require something a bit different. We'll simply demand that probability that h of x not equal to hs of x not equal to f of x is less than or equal to delta.
So can you please repeat this? What highlight the difference between a concept class and hypothesis class?
So the concept class is where the ground truth is drawn from. All right. So the assumption is that x is randomly drawn according to distribution px, whereas the relationship, how you get y from x in the ground truth can vary. Either it could be according to some conditional distribution py given x, or there could be a deterministic relationship, that is y is equal to some f of x. And this f is assumed to be drawn from some class of functions which we call the concept class. So the concept class inherently deals with the ground truth, which you may or may not know. The hypothesis class is where you're drawing the functions for your learning algorithm, the class of predictors. So the hypothesis class could be class of all neural nets, or class of all linear classifiers, class of all kernel classifiers, so on. All right?
Sir, is R of HS empirical loss?
No, R of HS is the, I've not talked about empirical risk so far.
So all of the R's here are generalization loss.
All of the R's are generalization errors.
Both HS and H star have to belong to hypothesis class.
Correct.
HS and H star.
Yes, both HS and H star have to belong to the hypothesis class. HS is something that is output by the learning algorithm and therefore is a function of the data set, whereas H star is the minimum possible within the hypothesis class and obviously is independent of the data set. Any other questions? Okay, so
This means equivalently that we can achieve zero approximation error.
you can achieve if you're talking about classification in the context of let's say binary or KRE classification, then you can actually achieve zero approximation error.
Okay, for binary. Okay, but
For classification only. I'm not saying that this is true.
concept class is back variable. It means that in everything.
So in general, for a general learning problem, then this is what we use. If you're talking about classification, specifically classification, then this is the definition that we will use for back learning of a concept class. The reason why I'm distinguishing between the two is that this may be possible generally only if the output alphabet, that is the label set, is finite. If the label set is infinite, then you can't really guarantee that you may not be able to ever achieve zero approximation error with any positive probability.
It means that condition will fail, the above one.
So this may fail. You may never be able to make this to be arbitrarily small if the label set is infinite.
Okay. I mean,
But this you can achieve. It's possible.
I mean, the second condition should be derived from the first condition, right? Because first condition is the base lemma, while second is the follow for a special case of classification.
Correct. So in this case, this is basically obtained by setting epsilon to be equal to 0.
Why
In a
do you say
sense.
that epsilon equal to zero?
Which one?
Yeah, for classification.
That's because you may be able to achieve the same
Zero.
risk,
0%. 100%.
100% accuracy, because the label set is finite. Right. If, let's say, the label set is infinite, then you can't have these two to be exactly equal to each other, even if the number of samples is infinitely many. Right.
So is the R star does not depend on the hypothesis class. The
So
R star, I think previously.
Correct. So the base risk does not depend on the hypothesis class. Right, so this is what I'll call the base risk. Any other questions?
So while the path learning concept class, we took H equal to C. H equals
That's what I say is, so basically this is what is called the realizability assumption. So when I say pack learning a concept class, it means that you can actually realize F somehow because you have some prior knowledge. If not, you can always use this general definition. Right? This general the definition of general pack learnability always holds, which is okay. But in fact, the specialization comes here, that you can actually achieve 100% accuracy. In the general case, you're never targeting 100% accuracy. Right? You always allow some epsilon positive and delta positive, but these you should be able to make these two arbitrarily small as you increase the number of samples.
Is it always the case that from the classification we get 0 error?
If it's a concept class, if you have the realizability assumption, then you can hope to get this.
But it means that the probability of misclassification is small.
Correct.
That doesn't mean that error is 0.
Which one?
In the classification,
Correct.
we are looking at the probability of misclassification is small.
Correct. But this can effectively be driven down to 0. Right.
This is star is R star.
In this case, R of H star is equal to R star, yes. All right. So as an exercise, you can think, we've seen a little bit of this earlier when we're dealing with concentration inequalities, where I talked about an application of the Chernoff bound for Bernoulli random variables. But even otherwise, you can try it even without that. You don't really even require a concentration inequality, but you can in fact show that every finite concept class is pack learnable, again under the realizability assumption. Say binary classification and realizable.
So I think the reliability assumption shouldn't be restricted to H equals to C. I think H can be C must be subset of H.
Sure, yeah. But that's fine, yeah. You can assume that. But really, here I'm referring to pack learning of the concept class itself. The realizability assumption, I agree, it's enough to have H to be a superset of C. There's again, in fact, we will mostly be focusing on general agnostic pack learnability, but we'll see certain special cases. Places where pack learning of the concept class becomes important is just to draw certain analogies and sometimes to show that certain things are impossible. Because let's suppose that it's impossible to do let's say that h is equal to c, all right? So under the realizability assumption, if it's not possible to achieve packed learning, then it means that with that particular hypothesis class, you can't achieve agnostic packed learning. So any hypothesis class that is not packed learnable cannot be agnostic packed learnable. Because packed learnability means that the ground truth is only drawn from functions from H. So if you can't even achieve zero approximation error in the concept class, then with a more general Pxy, it's not possible to achieve an arbitrarily small epsilon delta error. All right. Okay. So earlier I pointed out this particular question: does there exist a learning algorithm that does, say, absolutely well for all possible problems? If you had no restrictions on the hypothesis class that you were allowed to choose, then can you always achieve zero estimation error and zero approximation error, or arbitrarily small estimation error and arbitrarily small approximation error? Because in principle, you could just choose your hypothesis class to be the set of all possible functions. Right? What's stopping you from doing that? Nothing. Right? So then, is it possible to design a learning algorithm that achieves an arbitrarily small excess risk? The answer turns out to be no. So if you don't have enough samples, then it's impossible to achieve an arbitrarily small excess risk. So this is a theorem that I will not prove, but we'll frequently make use of this no free lunch theorem to derive lower bounds on the performance of, let's say, on the packed learnability or agnostic packed learnability for certain hypothesis classes. So the no free lunch theorem, as the term says, there is no free lunch. You have to pay something in order to get something. So it says that consider, if you take any learning algorithm, on X, Y, L. So X is the alphabet, the domain set, Y is the label set, and L is the loss function. And specifically, we'll specialize the no free lunch theorem for the case where Y is 0, 1, which means that this is a binary classification problem. And the number of samples that you have is, let us say, less than the domain size divided by 2. Suppose that the number of data points that you have is less than half of the size of the domain. Okay. Then there exists some bad distribution Pxy, which will prevent you from achieving a small risk. So there exists a Pxy for which two things happen. One is that there actually exists a function that achieves zero error for this problem, for this distribution Pxy, but you will never be able to find that. So there exists some f belongs from x to 0 comma 1 for which the risk is equal to 0. So there is a perfect classifier for this joint distribution Pxy. But no matter what you do, the risk that your learning algorithm achieves will be greater than or equal to 1 by 8 with some positive probability. Right? So you take any possible learning algorithm. It doesn't matter what learning algorithm you take. And just to sort of parse this theorem a little bit, I've not defined a hypothesis class here. All right? So implicitly, the hypothesis class is either it could be the set of all possible functions or some other restriction. That's still fine. But it says that no matter which learning algorithm you choose, if the number of samples is not too large, right? If it's less than the size of the domain divided by 2 for a binary classification problem, then there will always be a joint distribution Pxy for which there is actually a function that achieves 0 risk, but your algorithm will not be able to find it. In fact, it will do very badly compared to this optimal predictor. Okay, yeah.
Is it always finite?
So let's talk about it just a little bit. Okay, but hopefully the statement is fine. Are there any questions with regards to the statement of this theorem? Okay, so this automatically means that if this means that if the domain is infinite, then there's always one problem over which you will fail. Right? Or if x is infinite, it is impossible to achieve R of Hs minus R star to be arbitrarily small. Again, if x is infinite, it says that it's impossible to achieve an arbitrarily small excess risk. So it's not possible to do absolutely well. But then if x is infinite, there is still the hope of doing relatively well. That is, you fix a hypothesis class, you want to be able to do well compared to the best within the class. This no free lunch theorem says that there exists a function over the space of all possible functions from the domain to 0, 1, not from the hypothesis class to 0, 1. All right? Questions?
So it means that the main set is infinite pack learnable.
No, so that's the difference, right? So pack learnability only says how well can you do within your hypothesis class. Your only goal is to achieve an arbitrarily small epsilon and delta compared to the best within your class. The no free lunch theorem says that there is some arbitrary function from the set of all possible over the set of all possible functions from x to 0, 1. So yes, if you choose your hypothesis class to be the set of all possible functions from x to 0, 1 and x is infinite, then this hypothesis class is not pack learnable. But if x is infinite, but your h is not the set of all functions from x to 0, 1, then there is still the hope of being pack learnable. If you choose your hypothesis class to be the set of all possible functions, then it is not pack learnable. You're right in that sense. So that is why if you're trying to design a learning algorithm and your domain is infinite, then you should never choose your hypothesis class to be the set of all possible functions from x to 0, 1. You should restrict your hypothesis class. And indeed, what is actually happening is, in a sense, overfitting. The class of all functions is too rich. There is some function which is optimal, but then you will not be able to perform well because no matter how many samples you have, the function class is so rich that you will always overfit and you will do badly compared to, you will do badly when it comes to the generalization error.
So can I say that is a x by 2 is a tightest upper bound?
No. It's not any tight upper bound at all. It is something loose. And in fact, even these quantities 1 by 8 and 1 by 7 are something that are arbitrary. These are not necessarily the best possible constants. These constants are chosen just to say that you can't make epsilon and delta to be arbitrarily small. It could have been 1 by 16 and 1 by 25 for all I care. Doesn't matter. Something positive.
I think that it would be better if you mention that HS belongs to all set of functions instead of.
So HS could in general be drawn from some restricted, so because I'm not saying anything about the learning algorithm. The learning algorithm could implicitly use a particular hypothesis class. But then the comparison being made is with respect to the optimal function from the space of all possible functions. So this is a statement that is being made about the excess risk, not the estimation error. Right? So this is the excess risk, and this is the estimation error, and this is the approximation error. The no free lunch theorem is saying that you cannot make the excess risk to be arbitrarily small if x is infinite, for example. The definition of pack learnability for a hypothesis class to be pack learnable, this is a statement purely about the estimation error. For that hypothesis class, the approximation error could be large, and therefore the excess risk could also be large. But the estimation error can be made small. All right, does that?
Like since I am assuming that estimation error and approximation error will be positive,
Okay,
non-negative. So if excess risk can't be brought down to 0,
correct.
it means that estimation error and approximation error also can't be brought down to 0.
That's not necessarily true. It means that both of them can't be simultaneously brought down to 0. But it could be the case that I tolerate a slightly large approximation error, but I want my estimation error to go down to 0. It is possible to achieve 0 estimation error, non-zero approximation error, and non-zero excess risk. Right? Any other questions? Okay, so right now we're just building tools. We'll later on see how the no free lunch theorem can be used to derive lower bounds. But then that's the no free lunch theorem basically gives a negative statement that something is not possible. But on the other hand, what can we say about what is actually possible? When is it possible to guarantee pack learnability? Because remember, all of these terms, the generalization error or the risk, these are not quantities that you can calculate, right? Because after all, in the end, you have a data set. And whatever you do, you can only calculate with respect to the data set. So given the data set, you can't really say a priori how small the generalization error is going to be. But still, pack learnability says that given a certain number of samples, you can always ensure, even though you don't know the actual distribution Pxy, you can ensure that the generalization error is not too far away from the best possible generalization error within your class. All right. So most of these results on guaranteeing pack learnability are derived using this notion of uniform convergence. What is uniform convergence? It basically says that given sufficient number of samples, the empirical risk is going to be arbitrarily close to the generalization error for every hypothesis. Okay, so let's define. So a data set is said to be, say, epsilon by 2 representative if the following happens: for every predictor within your hypothesis class, the empirical risk is epsilon by 2 close to the generalization error. So this is nothing but 1 over n times summation I equal to 1 to n L of yi h of xi. So given the data set, you evaluate the losses on all of the samples in the data set and take the average. So the average loss within this particular data set is equal to the generalization error, which is the loss on an independent and identically distributed sample. Okay, so a particular data set is said to be epsilon by 2 representative if the empirical risk is close to the actual risk, is epsilon by 2 close to the actual risk, and this happens for every single hypothesis within your hypothesis class. Now, it may or may not be possible to get an epsilon by 2 representative sample, but if we are actually able to get an epsilon by 2 representative data set, then things are good, because
So that R of H should be R of H star, right?
which one?
R of H.
No. So this is close for every H. So basically, suppose that I evaluate the empirical risk for every single hypothesis within the class. Then the value of the empirical risk is close to the generalization error for that particular predictor.
But I think by using primary recursion, I can get the same
Exactly. So we'll see that if S is epsilon by 2 representative and let's say we choose HS to be the empirical risk minimizer, which is R min overall H one by n L of yi comma H of xi. So henceforth I'll refer to this particular quantity, the empirical risk, as Rs of H, where this subscript S will be used to denote that this is the empirical risk. Alright, so if S is epsilon by 2 representative and Hs is taken to be the empirical risk minimizer, then R of Hs, the generalization error of the empirical risk minimizer, deviates from the optimal risk by an amount at most epsilon. In fact, I don't even need this mod. And this just basically follows from triangle inequality.
So when you're fixing the way empirical risk is derived, or in this case we are saying that empirical risk
Uh-huh.
is equals to R min of this,
Correct?
it means you're fixing the learning algorithm.
Correct. This is one learning algorithm.
So that previous lemma, that epsilon by 2 representative,
Correct? Which one? Here.
this definition.
So this definition has nothing to do with learning algorithm,
But we are saying that is
right? So this is a property of the hypothesis class and the sample. Right? There's no algorithm in this definition. For a given hypothesis class, we'll say that a particular sample, particular data set is epsilon by 2 representative if the empirical risks all approximate the true generalization error.
it means it for the next lemma won't hold true for any other learning.
So what this lemma is basically saying is that if your data set is a good representative, then ERM is a good learning algorithm. Right? That's all that it is saying. So if you magically got a data set, is a good when I say good, whatever, an epsilon by 2 representative where epsilon is sufficiently small for this hypothesis class, then empirical risk minimization is a good learning algorithm. And the point to be kept in mind is that this definition is a property of just the data set. And of course, the hypothesis class H. It has nothing to do with any learning algorithm that you may want to choose. So if you are able to get a good representatives, then ERM is a good learning algorithm. If it's not, then ERM may not perform well. All right. So then if we can somehow show that if we can show that the probability that S is not epsilon by 2 representative, if this is, say, less than or equal to delta, then it means that ERM is a pack learning algorithm. Right, this is good enough. And in fact, this is the approach that we will use. All right, so when we want to, let's say, design an algorithm, we'll exclusively focus on ERM or a variant of ERM. But when we want to prove lower bounds, we want to show that no matter which algorithm you choose, you will not be able to achieve a target accuracy. Okay, any questions?
Is it, yes, is epsilon by 2 representative is not representative? It is not epsilon by 2.
Correct, S is not epsilon by 2 representative. So basically the probability that the sample is not a good representative is arbitrarily small. If this can be made arbitrarily small, then it is pack learnable. Or maybe the positive statement would be the probability that S is epsilon by 2 representative is greater than or equal to 1 minus delta. For an arbitrarily small delta, then ERM is a pack learning algorithm. Where, of course, I mean, this is a loose statement where I can make epsilon and delta to go down to 0 as I increase the number of samples. That's a requirement. In the next class, I'll make this a little more formal by stating this property of uniform convergence. Effectively, what we want is that as the number of samples increases, the empirical risk converges to the generalization error. If that happens, then it is pack learnable. And in fact, most of the proofs for pack learning go through this route of uniform convergence. There are some other approaches, particularly a couple of papers that have come out in recent years, that try to do this without going through the route of uniform convergence, which potentially could be useful for a broader class of learning problems. Okay. Any questions?
So if S is epsilon by 2 representative,
Yes.
S is good representative,
Correct.
then why whole machine learning we just use cross entropy, band cross entropy, scale loss? Why did we never use? I mean, I haven't used ERM.
Effectively, you are using ERM in practice. In practice, most machine learning algorithms do use ERM, but with a different loss function. Right? Whenever you are doing, let's say, gradient descent, the gradient descent or stochastic gradient descent is performed over the empirical risk all the time. Maybe with a regularization term for reasons we'll see later, but effectively you're always trying to minimize the empirical risk at the heart of any practical machine learning algorithm. But in practice, you choose even though your goal may be, let's say, to minimize classification error, you choose a different loss function. Instead of minimizing the 0-1 loss, you instead try to minimize the cross entropy loss. And the reason for that is because the 0-1 loss is a nasty function. It's not smooth. Whereas something like the cross entropy loss is smooth. And therefore you can use gradient based algorithms like stochastic gradient descent or ADAM or ADAGRAD and so on to minimize the loss function. Because at the heart of it, if you want to solve for the ERM, you basically have to minimize this quantity, right? So then what becomes important is how efficiently, computationally efficiently can you perform this minimization.
Okay, just to digest, did you just mean that whole machine learning and deep learning which we are studying is just empirical risk?
Yep, a lot of it is just empirical risk minimization. A lot of them just do empirical risk minimization, nothing else. So a lot of deep learning and machine learning, like algorithms, many of it just boils down to how do you choose an appropriate hypothesis class H, and how do you choose your loss function so that you can perform this minimization efficiently. All right, so there are two parts of it. One is how do you do this efficiently, which is something that we will not worry about in this course. We will assume that you can somehow do this minimization exactly. But in practice, that's a major driving force behind choosing your loss function as well as your hypothesis class. Okay? All right, so let's maybe stop here and we'll continue in the next class.